All right, good morning, everyone. So welcome to the last tutorials. So today we'll do two things. One is we'll try to solve a couple of simple equations, and then we'll continue on yesterday's topic of simulation for the later half of the morning. All right. So let's consider simplest problem that we can do with making use of the active Brownian particle model is to try to calculate the long time diffusivity, right, in free space in 2 dimensions, the swim diffusivity. So let's just write down the equations that we have derived before.
Good job. Okay. I'm sorry. I can.
So in 2 dimensions, all right?
What?
Okay, so because we have the probability distribution, how do we calculate our mean displacement? Any suggestions?
What's up there?
So the mean displacement would be the average position, right? Averaged against the distribution. So then that means, yeah, right. So then if we say this is the mean displacement, that should be integral of x against the probability, right? Integrated over space and orientations. So that will be the mean position.
Oh.
So let's try that. So what I can do is I can multiply this equation here by x and do an average, right? So if I do that, what I get is from the first term here, and that's just average of x. And the second term, okay. And the last one, is this. So let's look at the last term here first. We can do the angle integration first, right? So what happens after we do that? Because the x is not a function of the angles. So we just integrate the second derivative. And what happens when we integrate over from 0 to 2 pi?
The details by 2. So isn't the third term same?
Yeah. We're looking at this term here. Any suggestions? Because t is a periodic function of phi, right? So what happens when you do the integration? It's 0. So the derivative is also periodic. So that is gone. So we're just left with the first 2 terms here. And this one we can also carry out the integral. So let's do the x integral first in this case, and then we're going to integrate over the angles. So what I can do here is I'm going to pull out the gradient in front of the whole product. But then I need to remove the gradient on x. Okay? The gradient of x is the identity. So that means I just need to remove j of t from the integral. So if I do this, and if you look at this term here, so what we have is, from here we have the integral in space, the divergence of a quantity, j times x, over the entire space, right? So we can apply divergence theorem once again. So this becomes an integral at infinity of the normal vector pointing out of infinity, got it with the flux x ds, the surface integral. So what happens to the probability at infinity? Or the flux? Because particles are getting conserved, so we can't have particles escaping out of our domain, which means there's no flux at infinity. So this is actually 0 as well, right, due to conservation. So that's great. Turns out then actually we have simplified our calculation quite a bit already, right? So what we have here, if we go back, okay, we have the first term. Let's write that down. And the second term that we have looks like it's just a minus, and the integral of the flux itself over space and the angles, that's equal to 0. Okay, any questions? That's good. Now we just let's write down the flux vector, which is there's a swimming part minus a diffusive part. Right? That's good. Okay, so we just plug that in there, and then we'll get the following equation. And I'm going to move the integral to the right-hand side. Okay? P dx phi. And then there's another integral, which is minus dt, integral of the gradient in space and in the angles. Again, we can apply the same theorem. So we have the gradient in space. So this integral becomes integral at infinity, the normal vector, times p ds. That's the surface at infinity, and then there's an angular integral. So what is the probability itself at infinity? Sorry? And the reason is?
Predictabilization.
Yeah. So we can't have particles be at infinity. The reason is, if you integrate the probability over entire space, that's normalized to a finite number. If you have a finite value of probability at infinity, that integral, the total particles wouldn't be finite. Because why? Because if you think about the volume or the length at infinity, that's unbounded. If you have a finite number times the volume element, which is going to infinity, you can't have a finite number. So you can't have probability at infinity, which is 0. So in the language of distributions, that's a compact supported distribution. The way to think about that, you visualize a Gaussian distribution, for example. If you go quite far away from the mean, there's nothing, and probability is 0. So that is always true for probabilities in free space. So this term is also 0. So we have a simple equation here. Right? And if we let's now just look at this equation in a little bit more detail. And one can say that, of course, this is the equation we get from physical understanding. Why is that? Because on the left-hand side, that's what is the quantity on the left-hand side. So I'm taking the time derivative of the mean position. What is that physically? So that's the net or average velocity of the particles, because we have particles that are swimming, and they also have diffusive motion. So what is the net velocity? It will be the net swim velocity, right, of the particles. So that's what the right-hand side is. So us times q, That's the swim speed or swim velocity, average over the probability. So that's the net swim velocity. So physically, that makes sense. And we
US.
that's the speed, the magnitude. USQ is a velocity vector, right? As a whole. Yeah. Other comments?
Should be an amazing velocity vector on space.
Sorry? Yeah, we're averaging because we're looking at the average, the net in the system. Yeah, or both space, both linear space and angular space. Yeah. Other comments? Okay, that's fine. But we haven't, because we don't know the distribution P, so we can't solve this equation yet. But I'm going to do one thing. So previously we were taking orientational moments. Remember, we look at the number density, polar order. Those are when we integrate out the orientational degrees of freedom. So I'm going to do something else here, which is I'm going to define a new quantity, say P naught, which is the integral of P just over space first, not over orientations. Okay, I can do that. That's the definition. So if I do that, what I have here is, because I've already defined this quantity, so that I can rewrite this equation in terms of P naught. Then I have Q P naught dq. Okay, all right. And the one question is, so I've integrated over space. So what does P naught depend on?
To make you.
So it still depends on Q, right? And time. Okay, good. So then if we look at this equation, what we can see is if you can find P naught first through some means, then I can solve this equation, right? So then now let's try to find P naught first. So P naught is just the integral of the probability over space. Again, we can go back to our equations to find that. So if I just integrate over space of this entire equation, I will get P naught. Equation for P naught, right? So if I do that, the first term is time derivative. And the second term again would be gone. So I'm integrating because I'm integrating the divergence of the flux. But at infinity, there's no flux. And the third term is just, I replace P by P naught. That's all. Right? So that would be our equation for P naught. Any questions? Okay, that's good. So let's consider, of course, now we can try to solve this equation because we can write this out explicitly. We have is in 2 dimensions, for example. That's just the diffusion equation in angular space. So let's try to solve the simplest possible example. Let's say that our initial condition, or at Q at t equal to 0, say that's 1 over 2 pi. So initially it's just randomly or uniformly random over the angles. And then what's the solution to P naught? The best way to solve this equation is to guess what's the solution that we get at all times. And you can also think about this physically. We're solving a diffusion equation. If the initial condition is already homogeneous, does the distribution change over time for a diffusion equation? It doesn't. There's no gradient. There's no diffusive flux, which means P naught is just a constant at all times. Of course, that's easy to verify. You put that into the equation, the derivatives are all 0, so it's satisfied. That's good. So then what we see here is, going back to for this particular initial condition, our equation for x becomes q times p naught, which is 1 over 2 pi, for example, in 2D, is 5. And that is 0, right? I'm integrating an orientation vector q in a uniform distribution. Question?
Reason of choosing the
No, that's just one example, because we're going to just look at the long-time behavior, which doesn't depend on the initial condition. Right? So we pick the simplest initial condition that we can have. So for this case, there's no net velocity because it's already randomly uniform. There's no alignment in the system initially. So that means there's no velocity. Okay, that's good. Question?
So, initially you are taking the vectors to one way to one.
Yeah. So this I've normalized all the densities. This is one particle.
Yes.
Yeah.
Initial condition doesn't matter.
It doesn't matter for long time quantities. For short time it does, right?
Yeah.
Yeah.
So can we get this comedy like mean vision Gaussian distribution of any some like
You could, yeah.
that case that also give the
It also gives
the zero base issues.
yeah. So if the distribution has symmetry in it, then it will also be 0.
Yeah.
Of course, for a long time it's always going to be 0. But for this kind of initially it's already symmetric, that it's 0 from the beginning. Whereas if you think about an initial condition where particles are just aligned, then they're gonna travel for some time before they become random, right? So that part, that transient part, is a function of the initial state. Yeah. Other questions? Okay, so essentially, if we revisit our calculation, we have average of x is the integral of x p dx dq, right? So we can also write this in the following way. So we can carry out the x integral first, as we did for p naught, and then leave the q integral for later. So we have this quantity here, okay? And this one, again, is a moment-like quantity, so that's a spatial moment. So we can define that as P1, which is x p dx, okay? Right, we can generalize this because P0 is integral of p dx. Then we can have P2, which we have 2 x's, right? So on and so forth. You can do that. There's a structure to it, which means the second moment, so that's a mean squared, by definition, that is xx times p integrated over space and angles. Well, I can do the spatial integration first. Then I'm just left with P2, right? dq. So that's nice. We can express these things in terms of these spatial moments. Okay? And then what we can do here, now then essentially if we can find equations for P naught, which we already have, P1, for example, P2, then we can solve those and get all the mean squared, or the third moment, and so on and so forth, as one would like. So that's what we can do. And I'm gonna do this one now. So we multiply the original equation by xx, right? And integrate, because we're trying to find the mean square displacement now. We already have the mean displacement, so we'll do that. And again, let's bring back our equations.
How do we have the needy?
How do we?
Have the things that we have said that.
We're trying to derive it. Yeah. We've defined it in terms of the distribution, but now we're trying to calculate what that would satisfy. So I multiply this equation by xx and I integrate in space. Okay, so now we get an equation for P2, right? Okay. And essentially here you would have xx times the divergence of this quantity, dx, plus the last term is always simple because the last term here deals with angular gradients, but I'm integrating in space. So I get just P2 equal to 0. So here we see that we get the same kind of structure. Previously, the integral we did is this one, right? Yep. So now we have two x's, but then the way to do that is the same. You factor out the gradient, and then you distribute it. So you subtract off the gradient with respect to xx. So if you do that, I'm not gonna do that here, but you can imagine if you have done that, then this you get terms like the following. You have a minus sign, right? Then you have jt times. So when you take the gradient of xx, you just remove one of the x's. You have another one left. And then, but there's the one on the left and the one on the right. So you have two terms here that come out. They're in this structure. So hopefully we can see that structure right now, right, from this. Yeah, and then this we can integrate again, as we did before. So then, what we have is xx is what we want to calculate. That is simply the integral of p to dq. It's the next step. So then we can just integrate this equation against q. Okay, that's the second step. So what we have would be, looking at here, we would have xx. And then I'm going to move these integrals to the right-hand side. Going to skip a little bit of calculation here. But then what we discover is the following. So these all come from, so one is from here, one is from here. dq plus, and there's another one which is the the translational diffusivity times the identity. Okay? So we see something interesting already. We have this part here, right? So that's the diffusive part. And which means this part must be giving some other contribution, which we know is the swim diffusivity at this point. Okay, so let's try to solve these equations now. So we need to, turns out we don't have to solve the P2 equation because if we integrate that out, and then I do need to find P1. So the equation for P1 is of the following structure. Q P0 minus the diffusive part. P1 equal to 0. Okay. And P0 we've taken to be 1 over 2 pi, right? It's always homogeneous over time. So now we want to solve for P1. Okay, good. So let me rewrite this equation for P1 by moving the inhomogeneous term to the right-hand side. Okay, so I can write this out. The right-hand side, that's us 1 over 2 pi times the q vector, right? That's good. So let's look at this equation here. So on the left-hand side, what do I have? I have a diffusive equation, but with a non-homogeneous right-hand side. And the other thing we need to know here is the following. So we now want to try to solve this equation. And here's something that we know that can help us in solving this equation. So if we take the orientational Laplacian of q vector, what do we get? Well, we don't know yet, so let's try that in 2D, right? Simplest case in 2 dimensions. Again, if we draw our sketch for the orientation space, x and y. So q is in this direction here. Okay, so that can be represented by a single angle phi. So what is q in terms of x and y? So q is cosine phi in x direction, right? Sine phi in y. The gradient we know as well, so that's just the phi derivative, which means we want to take two derivatives of q. Now let's take the first one. Take the first derivative. What we get, well, that's minus sine phi cosine phi. Okay, all right, that's fine. And then let's take the second derivative. Well, minus sine phi becomes minus cosine phi. Cosine becomes minus of sine. So both terms have a minus sign in front. So I'm going to factor that out. And I get cosine phi sine phi. But that is q, right? So that's actually minus q. That's very interesting. Which tells us in 2D, the Laplacian, orientational Laplacian of q is minus q. Okay, right? So there's a general formula for this, which in general, or essentially in either d equal to 2 or 3, what we have is the following equation. So the Laplacian of q is minus d minus 1 times q. Okay, so when d is 3, you actually have a factor of 2 in the calculation. Okay, so that's something we'll make use of. Question. Sorry? Here? Yeah. I'm gonna share the note later on, so you don't have to write down everything. Just to other comments? So let's go back to the equation we're trying to solve. We're almost there. So I'm solving this equation here, right? Okay, good. And I also told you that if you take the Laplacian of q, you get q back. So what does that mean? I mean, q is a eigenfunction of the Laplacian operator, and d minus 1 is the eigenvalue. Okay, that's fine. And then let's just look at this equation. So on the right-hand side, I have something times q, right? Well, for that equation to hold, on the left-hand side, I should have the same thing, some number times q. But I also told you that the Laplacian of q is q itself, which means we can guess a solution for P1, which should be something times q, right? But that quantity should be a function of time, because on the left-hand side I have a time derivative. So let's just say that's a of t times q. So that's one possible solution here. Let's see if that's okay. So if we put that into our equation, what we get is a dot, that's a time derivative, times q minus dr a, and the Laplacian of q is, say we're in 2D just for simplicity, but this works in both in any dimension. So that's minus 1q, right? So there's a minus sign. Q is speed over 2 pi times q. We can cancel out q here. So I'm just left with a dot plus dr times a is equal to this number, right? So that equation we can solve. That's the first order ODE for A, right? Any questions? Okay, so this we can solve. I'm not gonna derive that here, but what you can imagine is you see the structure of the equation. You have a dot plus some number times a. So this thing gives rise to exponential decay. Question?
In the version 1 step of the what possible scenario checks. where it's supposed to be alpha p. It's always a vector.
Q is a vector.
It's like you use the probability that.
No, this is P1. P1 is the.
It's a vector.
That's the integral. It's not the original P. It's.
Okay.
So if we go back here.
Yeah, I get it.
Okay, so it's this guy here, right? So it's not the original. But we've already taken some spatial moments of it. Yeah, it's a spatial moment. That's right. It's for a spatial event. But here the algebra is not important. It's the structure of the equation, right? We have a dot plus some number times a. Or if we don't have the right hand side, what we have is an exponential decay, right? And 1 over dr, which is tau r, that's the time scale. That of course makes sense because any order decays over time is by tau r. Okay, so that's good. So in general, we can solve it, and I'm going to write down the solution here. So that would be speed times tau r divided by d minus 1. I'm going to write down the general solution in both 2D and 3D. 1 minus e minus d minus 1 t over tau r. So here, d again is 2 or 3, right, usually. And what is this s here? S is the volume of orientation space. So in 2D, that's 2 pi. In 3D, that's 4 pi. So that's a general formula, but the structure you see is just exponential decay on the time scale of tau r for A. Questions? But from this, we would have our displacement equation for the mean squared. Let me bring that back here. So go up to find this equation. Right? So now we have P1, and we just do the integration to find out the mean square displacement or the derivative of it. So then there's another calculation we have to do, which is Q times P1. P1 is a function of time times Q dq, which is A is again has nothing to do with the integral. So we just need to calculate QQ dq. Okay? So you can write out Q explicitly in 2 dimensions, and then you can do the integration. But here's a quick trick that we can do. So I want to calculate the integral of QQ dq. Now, Q is the orientation vector, right? Essentially, we're averaging over a probability distribution that's 1, that's homogeneous. So, which means this integral is isotropic, has no directional preference to it. Okay? But this is a rank 2 tensor, which means we should get a rank 2 tensor that's isotropic. And there's only one such tensor, which is the identity. Okay, so just by geometry, we can conclude that this has to be some number times the identity tensor. Okay, of course, we're not done yet, but now let's take the trace of this equation. So what's the trace on the left-hand side? The trace of a matrix is you add up the diagonal. Okay, so the trace of this would just be q dot q, right? dq. So what is q dot q? That's 1. So I just integrate 1 over dq. On the right-hand side, the trace of the identity tensor is the dimensionality in space. So that's d times this number. Well, so this integral is just the volume of the rotation space, right? So I've defined that as S. So that's equal to d times this number. So therefore, I can find this number, which is S over d. So then QQ dq is S over d times the identity tensor. Again, that's a relation that's true in general, regardless of the dimensions. So that's good, which means we're done with our calculations. What we have is now we put everything back there. And what I'm going to do is I'm going to take a 1/2, then the derivative of xx. I'm just going to look at this at long times. So I'm going to kill the exponential term. So what you get is precisely the following equation, which is dt plus d swim. Yeah, one sec. Question?
I follow this argument.
Which part?
This QQ deficit teaching.
This one?
Yeah.
QQ is a rank 2 tensor. The integral that once you've done that, right? It's a rank 2 tensor. But this integral is nothing special because it's a spherically symmetric. There's no directional preference to this tensor. Is that correct? Does that make sense? Which means it has to be equal to a tensor that's spherically symmetric. And that's the only one is identity. And that's the definition of identity. It's any kind of rotation doesn't change it. So which means this has to be proportional to the identity tensor. But then the constant of proportionality is something we can find by, say, taking the trace of it. Because we can then get a relation. Taking the trace on the left-hand side allows us to get rid of the q's. Okay, so that's a trick. You can do this more laboriously by writing out the angle. Say in 2D, you have a rotation angle phi. In 3D, you write out the two angles, and then you're going to discover the same result. It's just that's more messy in terms of calculations. So okay, so we put all of these back into our equation here. Then we'll get our relation. At long times, we have the following equation. Okay? And that tells us, so the left-hand side, that's the definition of a diffusivity from mean squared displacement calculation. And on the right-hand side, that's the result, which is the swim part plus the Brownian part. So that's the quantity we'll be using in the lectures. That's how you can derive it. Okay, this is for t tends to infinity. Questions?
Just look them up. Big.
Okay, I think we'll just do this one example. So in your notes, there's going to be another example, which I'm going to share that you can look at later on. But we're done with our analytical calculations. And then we'll go back to coding. Did you guys look at play with the V-check model last night? We can spend a bit more time on that, but we have another problem we're going to try to implement today, which is active particles in a porous medium. So, question?
You calculate pieces for there was something that's order current.
So the order parameter, yeah, we looked at.
What is that? Share what this so you look.
Yeah. Okay, I'll write that down again here. So the order parameter we can look at is essentially the global or the system polarity. It's a global polar order. So I have particles here in the system. Each have their own orientations, potentially, right?
Yep.
All the way, say, to Q of n for n particles. So I'm going to sum over these vectors from 1 to n, qi. So I'm adding up vectors. So I get a single vector out of that. And let's just normalize it by n, so that is an average. So then I get an average q, right? Mm-hmm. So then the order parameter is the magnitude of this average. It's a global order, polar order. As an order parameter, so let's just take the magnitude of this average vector. So that would be our order parameter. The reason is the following. Suppose these guys are uniformly randomly aligned. So add them up, I get 0, right? Suppose all of these guys are pointing in the same direction. So Q average would be the Q of each of these guys. So then the magnitude is 1. So it goes from 0 to 1. 1 is maximum alignment, maximum order. 0 is completely random.
So, so this not the sum of all the using for a particular event.
No, this is a global system order.
Okay.
So adding up of all, of course, you can you can break up the system into cells. And then you can say, is there local order in the cell? Then you just average over that cell. That's also possibility. Then now you get a field, right? At the scale you're looking at, then you have a order within each cell, and then they're different. That's correct. That's also fine. But we're just looking at the system, no net order in the system. Yeah.
So,
Question.
what about then for the early activities?
Which model?
In the cap. Yes.
The V-check or?
With that, so again,
No, that's fine.
so when you look to know on the one, everything is seen as a local one. Isn't this from the case? Is I go from
Not necessarily, because the flocking mechanism has a radius of interaction.
Let's go.
Question?
I'm just saying that the skill is subjective is the see how when two works here.
You could, yes. Yeah, we haven't. Yeah, the point is, and if these guys eventually get close to each other, then yes, then they will all be aligned. But if the density is fairly dilute or they're fairly spread out, there could be two flocks that are doing their own thing, but they are far separated from each other, so they never sense each other because the interaction radius is a parameter that.
The thing is that I observed that like it's very similar. This will totally is different. So one thing is that the radius curve is more than the bulk slice.
Sorry?
The radius much smaller than the bulk.
You can make it large, then they will quickly flock. Right? No, of course, exactly. So if your radius of interaction is infinity, then they start flocking right away. Then your polar order jumps to 1 and then it stays here. Right? Makes sense, yeah.
one thing is that in fact is actually we are not considering that in random was wherever the station crossing like then here we're taking some variation of the encourage that the particular capital cycle. At each step we are updating it for each particle.
Right, yeah.
So suppose two of the particles, one for after some one iteration,
Yeah,
they have same direction, same orientation.
yeah,
They are in the quick can case, but possible case.
yes.
In that case, will they be collide or something?
Colliding. So in the simplest V-check model, we don't have particle interactions, which means in the simulation they can occupy the same physical space. So of course you can add that into the model later on, but we're trying to work with the classical V-check model, where that's not included. But we can include it, right? We can include particle interactions within the additional potentials. Yeah.
It's alignment interactions of our particle interactions.
Sorry?
It's alignment interaction. And we say that they are also interaction.
They are. They're particles are interacting with. Yes. Yeah.
Over here, like we get it doesn't get anything to like a lot. We just already.
Because we didn't incorporate the collision, but you can, and first we could.
This is a phenomenological words.
It is all phenomenological.
Realities.
Yeah. Yeah.
So,
Good.
was regarding the radius. The radius is something that we use for our
Yeah, that's your input to the model.
squads. I think it should be its largest.
Ideally, what you do is you go out there and you say you want to follow birds, right? You measure their radius on interaction.
And usually they get different radius and different workloads.
Of course, yes. And so you observe large system, you can see, what's a typical flock size. That would be your radius, right?
Of them.
Yeah. Yeah. Other comments?
Spot. Okay.
Okay, so let's try one last simulation problem.
It's defined. If we cannot have an experimental question, then we do that here. and use some parameters which you tested, which increasing the radius size,
Okay.
and then see where it stabilizes.
Stabilizes in what sense?
In the properties in some sense. So maybe
Because they're flocking, so often there's no state,
but it is so.
right?
So what do you have such a pleasure? Like,
That's not pointless. The point is you don't necessarily have a steady state, right? Which means you steady state you take an image of the system. Take the image at a later time, it's the same, but now they're always flocking around, so it's not steady. But you can still talk about steadiness in the sense of your order parameter, okay? Even though they're all aligned, they're flocking around. Either each individual orientation vector but they're all pointing in one direction, right? They're all swimming in one direction, even though spatially they're moving around, but the system order parameter has been steady.
So it's order.
Yeah, it would be one.
Yeah,
But they're just going in one direction. So you can talk about steady nonsense.
so
Yeah.
in that sense, suppose we did but in functions, one is the radius, we are increasing the radius, how we are checking this habits.
Yeah.
And then we are seeing that at what point
Yeah. So are you thinking about a plot of the system order versus the radius of interaction? Yeah, that's something you can observe. Yeah.
optimal radius
Yeah.
beyond which if we was getting by our this gets expensive.
That's right. So you can imagine in that case, there's a critical radius where all particles are gonna be completely aligned, flocking in one direction.
Or but beyond that radius, if even if we increase the radius, it
Doesn't do anything else anymore because they're already aggregating close to each other. They're already fully aligned. Right? That's all they can do at most is fully aligned.
so like, it is like what aspects here when we are seeing the orientation order,
Yeah.
which is this the summation of silence square, like the summation of possible,
like pretty obvious.
like
Summation of
like with Q there is a long like with that.
This thing. Like,
Yeah, we have to take out
everything should like that is the advertisement.
the average vector.
yeah.
And very high like quantities all order. The phi will be same for all the particles.
Yeah.
So we need to science spec factors person, which is
Very
very
wild.
Yeah, that's the system order multiple is one. That's fully aligned. Yeah. Yeah, exactly right. Yeah. Yeah, because the other extreme is they're completely random. Then your average your vector is zero, so the norm is also zero. Yeah. But again.
Good.
Okay, let's do one final simulation example. Trying to find that here. I'm gonna just explain this briefly. So you want to think about again, let's go back to a single particle, okay? Just for demonstration. Active particle in a porous medium, something like this. So we're going to take a square lattice of these obstacles in space. So they're repeated indefinitely. But in simulation, we don't have to do that. We just have to take a unit cell, like the one I drew here, right? So you see on the four sides of the box, you would apply a periodic condition. So when the particle moves out from the right, you put it back in from the left, and so on and so forth. And you see there's an obstacle in the middle of the simulation box. So that we've done already before in the opposite sense, where we look at particles inside a circle. Now it's outside, which means to resolve the collision with the boundary there, what we have to do is the following. So now it becomes, if x is less than the radius of the obstacle, you move it to contact. But the movement is the same rule as we did before, right? So that you make sure the particle doesn't get into the disk in the middle. And then the other thing is you want to make sure, suppose that the length of the box is 2L on each side. So you want to make sure the radius of the disk is smaller than that of the box, so less than L. Otherwise, it wouldn't make sense geometrically. Okay? Questions? Yeah.
Instead of this periodic boundary that is, what does it mean physically?
physically means if you don't do that, you have to keep track of the whole system, right? So you would label all your pillars in X and Y direction. Say the one in the center is 0, 0, then there's a 0, 1, there's a 1, 0, and so on and so forth. So you have to keep track of all of those.
So, then we can think it also topology.
Yeah, it's a periodic geometry. That's why we can do that.
Because I'm being a purpose with some.
Yeah.
So, and you say that they are taking one box and the whole space is just a copy of this.
That's what periodic means. Yeah. You tile entire space with the single box here. Yeah. It's just easier because especially when you think about handling polite collision with the disk in the middle, you can't just check with all the disks in the entire space. So you want to just do that for the main cell, and then when the particle goes out, you move them back in. But the other thing is you want to keep track of how many times they have crossed the boundary of the main cell. Because, for example, if you want to compute mean square displacement, you can't just use the coordinates that's being wrapped into the main cell. That's bounded from minus L to L, right? So the means there's an index in your simulation which keeps track of the total number of boundary crossing. For example, what you would do is you have two indices. One is in X direction, one is in Y. Initially, those indices are 0 because you start from the main cell. Now, suppose you take some steps, and then one particle moved out of the box from the right. So you add 1 to that index, indicating I'm actually in the cell number 1 in the X direction. But then you would write back your actual position coordinate into the main cell, okay?
And you can even insert number.
Yeah, so that's a cell number. And then later on, you would accumulate the index, okay? So now it's +1, but then after a few steps again, it moved out from the left. So you would subtract 1. So it's accumulating the index. Then the index at any time is always the net number of boundary crossings in X direction. Then to recap, to get back your absolute position, what you would do is you would just do the following. Okay, so let me write that out here. So you have your index, say that's Ix in the X direction. Okay, that's the total number of crossings, signed number. It's an integer, So you use that to multiply by the length of the box. Okay, in our case, that's 2L. Plus the coordinate in your main cell. So that allows you to unwrap it to get the actual position in the unbounded space, right? So that's all you have to do to get back the absolute position. Make sense? Other questions? So this is a very common, it's always used in simulations, especially when dealing with box systems without boundaries. In this case, we have boundary, but it's still a periodic structure. Yeah, so it's used everywhere. Other comments?
What are we trying to prove here? How they different are the one where we have used example here, the one that we use just then for one particle.
Because that is not a unbounded domain. It's an actual one circle. It's trapped in there, trapped in a cavity. Here it's moving around in space, except that you have spherical obstacles in space that you have to avoid. That's all. It's a different geometry. Particles now are outside the disks. These are obstacles, physical walls, right? In the example you talked about, you have particles inside this cavity, right? The problem is particles swimming here, right? They can't, these are walls. They can't get in there. Question?
So, and this porous media, it's a hard walls, right?
Yeah.
It's right.
We have to dig, write the simulation as it goes there, and there is no flux.
Yeah, that you can make use of the same principle as we did before, but it's opposite because you're outside.
Okay.
So instead, in addition to the periodic boundary condition, you would handle that as well, right?
So here, I would say that Here the walls are fixed, like
Yeah, because it's walls.
so.
Yeah.
But if we like from these, can we get idea about how big this hard sphere was? Like is it? Like can we get an idea of that? Like
Oh, because then the particles you want other particles to be moving as well, right? It's just walls. That's it. At the hard sphere, you're thinking about more than one particle. Both of them are hard spheres. When they collide, each of them get a force, and each one is gonna move according to that force. In this case, the boundaries, of course, they get a force, but they're not moving. They're not allowed to move. Yeah.
are there in this kind of hard space like synthetic system?
Yeah, you fabricate plastic beads. They're quite fun. They're well represented by hard sphere models. It's not a it's a real system. Yeah. Okay, so let's try to implement this. I'm gonna share the note here in case you need to look at the details. There's a few pages here, but I'll send it now. I guess it's also time for a break, so we'll come back
Like,
to try to do this exercise.